So here we go, this is our second section. As you're noticing, these videos are actually pretty short. That's because the concepts behind this aren't super difficult. It's, yeah, you just need to practice it. You're pretty good to go. So today is all about impulse. We'll dive into what that is, purposes, learn about impulse, solve some problems. Impulse. Guess what? I actually taught this to you yesterday. Impulse is simply the change in momentum. So if you calculate change in momentum, you've got the impulse. So remember the last question in the last set of notes, I asked what's the change in momentum? Ta-da, you solved for impulse already. So the equation for this is delta rho, so change in momentum, equals mass times change in velocity. And the part that is new today is this is also equal to F net times time. If you remember from yesterday, I told you the second unit for momentum is newtons times seconds. Here's where it comes from. So let's give this a go. Thor and Hulk are at it again. Thor takes his 8-kilogram hammer and swings it at 15 meters per second at the Hulk. How much force does the Hulk exert if he brings the hammer to a stop in 0.11 seconds? So here's our equation. Let's plug in all the numbers that we know. So remember, change in velocity is the final minus initial, just like the change in anything. So plug in some numbers, and we end up with F net being negative 1,091 newtons. Now, why is this negative? Well, it's negative because he's exerting the force in the opposite direction. So sometimes you might have to put the force as negative. This is something that is new. We didn't do this in dynamics or the forces unit. Sometimes you have a negative force, and that is okay. So the concept of impulse can be used to describe a few things. One of them is why seatbelts or airbags in your car help people sustain less damage during a collision. So if we look at this equation, we can talk about what happens if you have a seatbelt and what happens if you don't. So if you're wearing a seatbelt, your mass stays the same, okay? Whether you have it or not, that doesn't change. Your change in velocity also doesn't change, it's constant. So you can be driving at 50 kilometers an hour and go to a rest if you have a seatbelt or not. That's not what is going to change. What does change though is when you come to a stop, the amount of time increases when you have a seatbelt. So consider this, if you get into a car accident, the seatbelt slows you down a lot longer than if you were to hit the steering wheel, it'd be an instant stop. So it takes longer for you to slow down because of a seatbelt. And looking at this equation, because mass times change in velocity is constant, if I increase time, that will increase the right-hand side of the equation. So the F net must decrease in order for you to still have F net times time equal the same thing. So if you have seatbelts, it decreases the amount of force because it increases the time it takes you to slow down. That's the idea with that. So more time to slow down means less force required. Let's look at another scenario like this. Why is it important to follow through, so to continue your swing? In sports like football, you swing your foot all the way through. Baseball, you swing the bat all the way through. Tennis, you swing the racket all the way through. You don't just hit the ball and then stop. You're told to follow through. So why does this actually help? So again, using this concept of impulse, let's take a look at what happens to the ball in each of these cases. So your mass doesn't change with the ball. Okay, whether you follow through or not, that's constant. The amount of force you exert doesn't change. What does change is when you follow through, you're in contact with the ball longer. So the amount of time increases. So if time increases, the right-hand side of this equation, the number gets bigger. Therefore, your change in velocity gets bigger. So this is why following through helps, is because the more time you're in contact with the ball, the greater the change in velocity. So the bigger the change in velocity, the better it is with sports. Usually, not always, but for the most part. So that's why you're told to follow through with your swing. There you go, that's impulse. Pretty straightforward. You got an equation, solve stuff. This one's from Fast and Furious. Surprise, surprise. I'm just gonna play this. You can see what you disagree with. Okay, so I'm not really an expert with high-powered magnets like this. I'm going to assume something that is possible, but there are a lot of things that are just not correct with this. So let's go through. Okay, so this part, you know, he flips on the magnet and it pulls the two beside them. Okay, this one I can actually see as working out. We're going to ignore the fact that, you know, if they're really that powerful, they should also be pulling the metal that's in the car inwards as well. Let's suppose that you can make it a magnetic funnel and actually channel in a certain cone of influence. Then we can assume, yeah, even the stuff that's beside the car, like the metal sides of the car, should also be pulled in. Now this part, less realistic. You know, if you're, so he's putting on the magnet, all these appliances are being flung out at the car. Okay, in order to do that, there isn't, according to Newton's third law, you've got equal and opposite reaction force, right? So if the magnets in the car are pulling all these objects with such a big force, that force is also going to be applied on the magnets within the car. You don't see the car moving at all. The other part here, that is quite ridiculous is this part where, you know, they turn on the magnet and guess what? It ignores all the metal except the very specific metal that is on this guy's armor, whatever. That's the only thing that gets pulled by the magnet. That's very interesting. Again, same thing here. She launches this truck up in the air. According to Newton's third law, in order for that truck to be launched upwards, there needs to be an opposite force acting on the magnet. And so that should have squished her car into the ground. So, cool, interesting scene with magnets. Very unrealistic with Newton's third law. And yeah, you can't intentionally select certain metals to be pulled. That doesn't make any sense.